Okay, let's get started. This is an interesting session following Mahak and Gohan's presentation. So for the people who missed the last presentation, I will give you a very high-level summary of what has been achieved in SONiC community. And for the one has been here, this is a pop quiz, how much you remember. This is Xin from Microsoft. I have Wei from NVIDIA join me. So the session will be looking back, a little bit about looking back, what we have done, and what has been shown in the data center, and then lesson learned, and looking forward. Okay. So last year, it's very fast, seems like yesterday. Wei, Gohan, and me were here talking about looking at AI networking, AI coming, right? What could be the challenge? And what we plan to do. So this year, we are here again to look at the challenges. So in addition to the power, intelligence of the model, the hardware evolvement, right? I'm talking about network challenges, the bandwidth to enable the fast, the large amount data transmission for the AI inferencing training, so that the network will not be the bottleneck of the evolution of AI era. Number one challenge. Number two challenge is because the AI traffic and model and the special characteristic of the how AI model works, the reliability, fast failover requirement to the network is much more stringent than the traditional network. That in the last presentation, they also mentioned that. In that sense, the application level would like to know how far, very quickly, when the failure happens, the link failure, link flap, could be tolerant. For the regular traffic, now will be challenging for the AI traffic. So we're also looking into the telemetry visibility area. When coming back, when we build a large network, long blocking for the AI traffic to connect an ocean like GPUs together, right? How do you maximize, most effectively use all the paths we build, all the network paths for them? Is also a challenge. That's called advanced load balance. At the end, we saw that end-to-end optimization from the host to the link to the devices. Optimization will be the best for the AI network. If we look to the next page, so what we have done. So first of all, in the last year to now, right, we have evolved from 400 gig to 800 gig switches, able to run SONiC and enable the AI traffic on top of it in production, provide a long blocking network for the large pool of GPUs. Second, I will be very fast because the last presentation has gone down the detail application, implementation details to this, but I'm going to pull you back to see why we need this. Then for the routing part, because of the application, AI application different from the other, unlike other traffic owners, they would like to have the capability to understand the route, have the ability to understand the failure, so that they have the control of what to choose and what's the best for their model. So that in this, we enabled segment routing, V6, for the application to be able to quickly understand the network topology, able to understand how to fail over, and to react, to decide, make a decision themselves. What's the best route to choose? Packet training enable us to resolve the problem of fast failover, to be able to reduce the detection of failures even less than 1 RTT. without retransmit, without to wait for the whole RTT NAC to be coming back, we are sending the trimmed packet, right, to notify the server, the sender, that there's a failure. Please react fast. And in order to be able to leverage effectively the large parse, like thousands of parse that one GPU actually can choose to your destination, that packet spray, right, is used to able to quickly load balance, to quickly choose the other paths, to be able to leverage all the multi-paths in a more effective way. Of course, this feature is mostly on the leak side, supporting from the switch side is also there. Last but not least, right, we are pushing the telemetry failure detection to a new high level. Instead of minutes, it has to go down to microsecond, so that application can react much faster, so that all the training will not be delayed. So today, what we have, based on this, Microsoft built so far the largest scale AI network based on Ethernet backend in Wisconsin. This is in our blog. It has 315 acres. It has 1.2 million square feet under the roof. What it does, it has all GB200 GPUs with liquid cooled. It can process one rack. This is not the whole GPU. Only one rack is able to process 865K tokens. And it has 1.80 terabyte between GPU to GPU bandwidth. The read-write per second to the blob is 2 million per second. So also within these last several months, the evolution of AI, right, also enable us to increase the fiber footprint by 40%, our WAN capacity by 20%. Instead of years, it has been shrinking to just the next 1 year to support this AI network. So with that, I'm going to give way to talk about lesson learned.
Yeah. Okay, thanks, Xin. So in the past 1 year, Microsoft and NVIDIA team work very closely to deliver several critical features for the AI networking. So I'm going to share 2 lessons that we learned from this journey. So the first lesson is very philosophy. So despite the big pressure, right, the pressure to deliver a lot of features in a short time window, we found that we can only deliver feature efficiently after 3 steps. First, we need to have a very rigorous spec of the feature, which consider all the corner case. Second, we need to clearly define the telemetry, like, for example, different counter, to monitor the different behavior of this feature. Last but not least, we need to have a verification plan to prove the implementation strictly follows spec and considering all the corner case. I'm going to use an example to show what I mean. Okay, so packet trimming is probably one of the most popular features that people have been talking about this for a long time. So the key idea of the packet trimming is that, so in the packet trimming there are 2 queues, right? Data queue and the trim queue. So when we use out the buffer in the data queue, so we trim the packet which can now be put into the data queue. Because the packet is trimmed, so we put this smaller packet into a higher weight or higher priority queue called the trim queue and for this packet. So we want this packet to arrive at the receiver side, so receiver side can send the loss notification to the sender, so sender can retransmit the packet as soon as possible. But one implicit assumption of this feature is that the trim packet will not be dropped. Unfortunately, this is not true. I'm going to show that the trim packet will definitely be dropped in certain scenario. For example, when your in-cast degree is large enough, for example, if you have a 4 KB RDM MTU and your trim packet size is 64 bytes. In this case, if your in-cast degree is larger than 64 and you run the traffic for long enough time, the trim queue will run out of buffer. In other words, even you trim the packet size, But when you want to put the packet 6 into the trim queue, the trim queue does not have enough buffer. So this trim packet 6 will still be dropped. So the next question is, okay, the trim packet dropped because the trim queue does not have enough buffer. So which queue we should attribute the drop trim packet to? It should be the original data queue, or it should be the trim queue. So this is the general scenario that trim packet will be dropped. I mean, regardless of the ASIC implementation, I can imagine that for different vendors, given different trim implementation, you may have different reason to drop the trim packet, right? For example, you probably have some PPS limitation. So when we deliver this feature, when we wrote the first version of the SI, we didn't take this corner case into consideration. Then we realized that, so we add lot of like trim drop counters into the set spec. So you can see more details in this PR. So this is a very, very important lesson that we learned. So even despite the big pressure, right, we should really consider all the corner case before we deliver a feature. So the second lesson we learned is about testing, is about quality. We found that the AI workload significantly raised the bar for SONiC testing. So as for today, the community tests heavily use PTF for function validation. The PTF is really good at checking the correctness. For example, if the packet is forward as expected, right? If the counter update as expected. But PTF is not good at measuring the performance. For example, throughput, PPS, or latency. And we found that the AI workload imposes, I would say, more stricter performance requirement. So we must validate both correctness and performance. For example, when we talk about packet trimming, right? If you use PTF, you cannot really measure what is the maximum PPS, the trimming PPS that one ASIC can support. So we believe that we need programmable, very high performance hardware tester to stress SONiC. Right? This is essential. So such kind of hardware-based network testing is essential to validate performance-sensitive features such as SRv6 forwarding, right, and also the trimming. So we noticed that today the SONiC management, the community test, the snappy test do cover a few cases. For example, traditional like RDMA feature like PFC and ECN. But we do need hardware tester which can scale to high port radius, because sometimes you not only want to saturate one port, you want to saturate all the ports of ASIC. We also need to define cross-platform hardware tester API, which can run on the top of different hardware tester, and we also want to have more such kind of test case to cover more features. So looking ahead, we believe that the bandwidth of the data set, the network bandwidth of the AI data center will keep increasing in the next several years. Right here, I list 3 types of network. Right, the scale up, scale out, and the front end. So we believe both of all of the 3 will increase. And to satisfy the bandwidth requirement, people are building more and more higher and higher bandwidth switch ASIC. So last year we talked about 51.2 Tbps switch ASIC. Now we are talking about 102.4 Tbps switch ASIC. So there are a lot of challenge brought due to the higher bandwidth. For example, we have our switch ASIC consume more and more power. So we need to have solution to improve the power efficiency. Like now today, everyone is talking about the CPU, right? Also, cooling is a big problem, right? We are talking about liquid cooling, immersion, even immersion cooling. And given the flatter AI network and the increasing switch ASIC bandwidth, we believe that we will have very large port radix in the future AI data centers. So such kind of large port radix bring a lot of challenge to the switch OS, such as the BGP session and also for the telemetry. So the SONiC should be prepared to handle all this challenge. The second vision I want to share is about inter-DC training. So according to the public information, according to Google's paper and OpenAI's video, the inter-DC training has come to reality. So both Gemini and the GPT-4.5, they are trained using the TPU and the GPU across multiple data centers. This means in the future, we need to design AI supercomputer, which can consist of multiple data center or even multiple regions. So this means we need to redesign our networking infra, and we need to think what role that switch need to play in this new type of AI supercomputer. For example, between the two data center or between the two region, right, we have a larger base round trip time due to the speed of light. So the feedback latency is really large. So what switch can do can reduce the feedback latency for, for the loss notification or for the congestion notification.
So at the end, right, just to summarize, this is a very exciting time. And networking, I think, is in the central piece of this AI era. The ones looking forward, we talk about the bandwidth, actually is not for 5 years, even not for 2 years. It's just next year. We see it's coming. And it will be very hard, it's alive for us to foresee for 5 years now. We can only see that far, right? Because everything changes so fast. Not only hardware generations, implementation from years to just months, iteration going fast. So we call for participation. Hopefully, you also feel the same excitement and feel like would like to be part of, or would like to be part of the community to resolve all these challenging problems ahead of us. Okay, so these are the contact information and where you can find us. Tomorrow there is another workshop at Google continuing SONiC, the similar topic, right? A different similar topic tomorrow. Looking forward to see you guys there. Thanks.